What if the reality you experience every single day, the solid ground beneath your feet, the passage of time, even the boundaries of your own consciousness, isn't what it seems? For centuries, this very question has haunted the greatest minds in history, from philosophers staring into the abyss of existence to physicists probing the fabric of the cosmos. Reality, as we perceive it, might be nothing more than an elaborate illusion, a fleeting shadow cast by forces far beyond our comprehension. And today, we're about to peel back the layers of that mystery, diving into 30 astonishing theories that challenge everything you think you know about the nature of existence. Picture this: you're standing in a room, certain of the walls around you, the air you breathe, the thoughts in your mind. But what if that room and everything in it is just a fragment of a vast, interconnected simulation? Or what if the universe itself is a hologram, with every event, every particle, merely a projection from some distant, unseen edge of reality? These aren't just sci-fi musings, they're serious hypotheses debated by scientists and scholars, each one unraveling the very foundation of what we call real. From the ancient riddles of Eastern mysticism to the cutting-edge experiments in quantum physics, humanity's quest to understand reality has led us down paths so strange they defy common sense. This journey isn't just about abstract ideas, it's about the profound implications these theories hold for our lives. If time is an illusion, does free will exist? If multiple universes bubble into existence every second, are there infinite versions of you making different choices right now? The answers might unsettle you, thrill you, or even reshape your entire worldview. So brace yourself, because over the next 30 revelations, we'll explore concepts so mind-bending, they'll make you question not just the universe, but your very place within it. Ready to have your reality cracked wide open? Let's begin. What if everything you've ever known, every memory, every sensation, even the laws of physics themselves, were nothing more than lines of code in an unfathomably advanced simulation? This is the spine-chilling premise of simulation theory, the first of our 30 reality-shaking ideas. At its core, the theory suggests that our universe isn't the base layer of existence, but instead a meticulously crafted digital construct, like an ultra-realistic video game designed by a civilization so advanced their technology is indistinguishable from what we'd call magic. Philosopher Bostrom laid the groundwork for this modern obsession with a now famous trilemma. Either nearly all civilizations like ours go extinct before reaching technological maturity, or they lose interest in creating simulations of their ancestors, or we are almost certainly living inside one. The math is startling. If even a fraction of advanced civilizations run ancestor simulations, the number of artificial realities would dwarf the one real universe, making it statistically likely we're in a simulation. Elon Musk summed it up bluntly: the odds we're in base reality, 1 billion to 1. But how would we even begin to spot the seams in this cosmic facade? Some point to unexplained glitches as potential clues, déjà vu, ghostly apparitions, or fleeting moments where physics seem to stutter. Others suggest quantum mechanics itself might be a tell, with particles behaving like processed data rather than physical objects until observed. The double-slit experiment, where particles act differently when watched, feels eerily like a program optimizing resources when no one's looking. Beyond the sci-fi thrill, the philosophical weight of this idea is staggering. If true, it redefines concepts like death, identity, and even morality. Are the simulators our gods? Do we have free will, or are our choices predetermined by algorithms? And perhaps most haunting of all, if we someday create simulations indistinguishable from reality, how could we ever prove we're not already inside one? The questions multiply faster than answers, leaving us staring into a digital abyss that might just stare back. Now imagine peeling back the fabric of reality only to discover the universe isn't three-dimensional at all, but a mind-bending hologram, a two-dimensional surface projecting the illusion of depth like a cosmic magic trick. This is the radical proposition of the holographic principle, a theory born from the fiery edges of black hole physics and string theory. At its heart lies a staggering idea: everything we perceive, stars, galaxies, even our own bodies, might just be information painted on the distant boundary of the cosmos, like a movie playing on the walls of an unimaginably vast sphere. The story begins with Leonard Susskind and Nobel laureate Gerard T. Hooft, who realized something astonishing about black holes. When matter falls into these gravitational monsters, it doesn't just vanish, it leaves an imprint, a kind of fingerprint on the black hole's event horizon. This sparked a revolutionary thought: what if the entire universe works the same way? Their breakthrough led to the AD-S/CFT correspondence, a mathematical dance between theories that suggests the three-dimensional world we experience could be a projection from a two-dimensional surface at the universe's edge. Think of it like a credit card hologram, flat when you look at it straight on, but bursting with apparent depth when tilted. But how could we possibly test such an outlandish idea? Scientists are hunting for the equivalent of cosmic pixels, tiny, grain-like structures in spacetime itself. The GEO 600 experiment in Germany and Fermilab's holometer have been scanning for microscopic jitters in reality, the quantum foam that might betray the universe's low-resolution underbelly. Even more bizarrely, some researchers suggest that anomalies in cosmic microwave background radiation, the afterglow of the Big Bang, could reveal imperfections in the holographic projection, like spotting the seams in a virtual reality headset. The implications ripple through every corner of existence. If the holographic principle holds, it means the universe operates like a quantum hard drive, with information fundamentally two-dimensional. Your memories, your emotions, the very sensation of touching an object, all might be shadows cast by data vibrating on some unfathomably distant surface. It blurs the line between physics and philosophy, forcing us to ask, is solidity just an elaborate illusion? Are we, in some profound sense, living inside a cosmic photograph? The holographic universe doesn't just challenge our perception, it redefines what it means to be real at all. There's a thought so unsettling it can make your grip on reality feel like sand slipping through your fingers. What if you're the only consciousness that truly exists? This is the razor's edge of solipsism, a philosophy so extreme it reduces the entire universe to a shadow play inside your mind. Picture waking up one day to realize every person you've ever loved, every sunrise you've admired, even the laws of physics themselves, are nothing more than figments of your own imagination. No other minds, no external world, just you, alone in the infinite theater of your own awareness. The roots of this idea stretch back to René Descartes' famous declaration, "I think, therefore I am." In his quest to find undeniable truth, he realized that while he could doubt everything, the existence of his body, the physical world, even God, he couldn't doubt the fact that he was doubting. The act of thinking became proof of his own existence, but here's the chilling twist. If all you can truly know is your own consciousness, how can you ever prove anything beyond it? This isn't just academic navel-gazing. It's a full-blown crisis of epistemology, the study of how we know what we know. Modern versions of solipsism take this even further with thought experiments like the brain in a vat. Imagine your brain removed from your body and kept alive in a vat of nutrients, hooked up to electrodes feeding you a perfectly simulated reality. Every touch, every taste, every emotional bond would feel real, but none of it would correspond to anything outside the vat. Now ask yourself, how could you ever disprove this scenario? The horrifying beauty of solipsism is that it's unfalsifiable. No experiment, no logic, no plea for common sense can definitively shatter its premise. But the implications cascade far beyond philosophy classrooms. If solipsism were true, morality would collapse into absurdity. Why care about others if they're just projections? Science would become a solipsistic diary recording one mind's hallucinations. Even language itself would be a paradox, a system of symbols invented to communicate with entities that might not exist. Yet here's the irony: solipsism's greatest weakness is also its most haunting quality. It forces us to confront how much of reality we take on faith. The belief that other minds are real, that the past existed, that the external world isn't a meticulously crafted illusion. In the end, solipsism doesn't just question reality, it holds up a mirror to the fragility of everything we assume is true. What if every choice you've ever made and every choice you didn't exists simultaneously, playing out in an infinite web of parallel realities? Welcome to the many worlds interpretation, a quantum theory so audacious it suggests our universe is just one page in a boundless cosmic library of alternate timelines. Proposed by physicist Hugh Everett in the 1950s, this idea doesn't just tweak our understanding of reality, it explodes it, claiming that every quantum event, every decision, even the flutter of a butterfly's wings, splits the universe into new branches, each one as real as the next. The roots of this theory dig deep into quantum mechanics' strangest puzzles. Take Schrödinger's famous cat, trapped in a box where it's simultaneously alive and dead until someone looks inside. Traditional quantum theory says the cat exists in a superposition, a blur of possibilities until observation collapses it into one state. But Everett flipped the script. What if the act of observation doesn't collapse anything? Instead, the universe splits, one version where the cat lives, another where it dies, both equally real but forever separated. The same goes for the double-slit experiment, where particles behave as both waves and particles. Many worlds argues the particle isn't choosing, it's taking all paths, with each possibility spawning a new universe to accommodate it. Critics argue this creates an extravagant, almost wasteful cosmos. Why should reality fracture endlessly just to avoid quantum ambiguity? Supporters counter that it's actually the simplest explanation, stripping away the need for mysterious collapse mechanisms. After all, if you accept that quantum states never resolve but simply branch, the math becomes cleaner, even if the implications are dizzying. Imagine a version of you reading this very sentence in a world where the internet was never invented, or where humanity colonized Mars decades ago. The theory suggests those versions aren't fiction, they're out there, pulsing with just as much reality as the one you're experiencing now. But here's the twist: if every possibility happens somewhere, does choice even matter? If there's a universe where you became a billionaire and another where you vanished without a trace, does the you in this timeline have any real agency? Philosophers wrestle with this, while physicists grapple with an even thornier question: how do we test a theory where every outcome exists, but we're forever locked into a single branch? Some propose hunting for faint echoes of other universes in cosmic radiation, or designing quantum experiments where parallel worlds might briefly brush against each other. Until then, the many worlds interpretation remains a breathtaking thought experiment, one that transforms the cosmos from a single story into an endless choose-your-own-adventure book where every page is being written at once. Consider this nightmare scenario. You suddenly wake up to the horrifying realization that your entire life, your childhood memories, the people you love, even the vast universe stretching around you isn't real. Instead, you're nothing more than a disembodied brain, spontaneously formed from random quantum fluctuations, hallucinating an entire existence for the briefest flicker of time before dissolving back into chaos. This is the spine-tingling premise of the Boltzmann brain, a thought experiment that takes the laws of thermodynamics and twists them into a cosmic horror story. The theory traces back to physicist Ludwig Boltzmann's work on entropy in the late 19th century. The second law of thermodynamics states that systems naturally evolve from order to disorder, but Boltzmann realized that given enough time, random fluctuations could momentarily create pockets of order in the chaos. In an infinitely old universe, these fluctuations could theoretically assemble anything: a cup of coffee, a galaxy, or even a fully formed, self-aware brain complete with false memories of a past that never existed. The frightening leap comes when you realize that in an eternal cosmos, the odds might favor such fleeting illusions over stable, long-lasting realities like ours. After all, why would the universe bother with billions of years of evolution when a single, momentary brain could hallucinate it all? Critics argue that if Boltzmann brains outnumber real observers, science itself becomes untrustworthy. How could we verify any experiment if our memories and instruments might be false? The cosmic microwave background offers a potential rebuttal. Its smooth, low-entropy state suggests our universe began in an exceptionally ordered state, making Boltzmann brains statistically unlikely compared to genuine cosmic history. Yet the paradox lingers like a shadow. If entropy eventually dominates, could our present reality just be a fleeting fluctuation in an endless sea of disorder? The philosophical implications are paralyzing. If consciousness can emerge from randomness, what does that say about the reliability of your thoughts? Could the very act of questioning this theory be proof you're a Boltzmann brain, manufactured with built-in doubts to sustain the illusion? It's a hall of mirrors where every exit leads deeper into uncertainty, leaving you to wonder whether the universe is a grand, enduring tapestry, or just the dying dream of a mind that never existed. What if the chair you're sitting on, the screen before your eyes, even the sensation of your own breath aren't material objects at all, but clusters of perception happening entirely within your mind? This is the radical core of idealism, a philosophy that flips materialism on its head by declaring reality to be fundamentally mental. While most of us instinctively treat the world as solid and independent, idealists argue that what we call physical is merely the steady rhythm of conscious experience, like a dream so consistent we mistake it for something separate from ourselves. The roots of this idea stretch back to 18th century philosopher George Berkeley, who famously declared, "To be is to be perceived." In his view, objects don't exist when unobserved. Instead, they persist because an infinite mind, which Berkeley called God, perpetually perceives all things. A falling tree in an empty forest makes no sound, not because sound requires an ear, but because reality itself requires a perceiver. Modern idealists have secularized this notion, suggesting consciousness might be the bedrock of existence, with the material world emerging from it rather than the other way around. Think of it like virtual reality. The headset isn't generating a world. Your mind is generating both the headset and the world simultaneously. Quantum mechanics adds tantalizing fuel to this fire. The observer effect, where particles seem to choose between wave and particle states only when measured, hints that consciousness might play an active role in shaping reality. Pioneering physicist John Archibald Wheeler even proposed the participatory universe, where observers literally bring the cosmos into existence through the act of perception. It's as if reality remains an unrendered video game until a player looks at it, forcing the system to generate the scenery. Critics dismiss idealism as solipsism's more polite cousin, asking how shared experiences like multiple people seeing the same sunset could exist without an external world. Idealists counter that individual minds might tap into a deeper, universal consciousness, like separate computers accessing the same cloud server. Others point to lucid dreaming as proof perception can construct staggeringly vivid worlds without physical input. The implications rewrite everything from morality to artificial intelligence. If reality is mental, does harming another's body matter, or is it the suffering mind that holds moral weight? Could machines ever be truly conscious, or would they just be complex illusions in our shared perceptual field? Idealism doesn't just challenge our assumptions, it dissolves the line between the world and the witness, leaving us to wonder whether we're inhabitants of reality or its very architects. What if consciousness isn't something that emerges from complex brains, but is instead woven into the very fabric of reality, present in every atom, every photon, even the vacuum of space itself? This is the radical proposition of panpsychism, a theory that dissolves the boundary between mind and matter by suggesting that all things, no matter how simple, possess some form of inner experience. Unlike traditional views that place consciousness solely in human heads, panpsychism imagines a universe alive with subjectivity, from the tiniest quark to the vast clusters of galaxies. The seeds of this idea are ancient, traceable to animist beliefs where rivers, mountains, and storms were seen as imbued with spirit. Indigenous cultures from the Amazon to Siberia have long perceived nature as a web of sentient relationships rather than dead matter. Philosophers like Plato and Spinoza toyed with variations of this concept, but it was 20th century thinker Alfred North Whitehead who refined it into a modern framework. Today, figures like Galen Strawson argue that consciousness might be as fundamental to reality as mass or charge, a basic property that doesn't arise from complexity but is always already there. But how could a rock or an electron experience anything? Panpsychists don't claim atoms have thoughts or emotions. Instead, they propose that even the simplest systems possess a bare whisper of subjective feeling, what philosopher David Chalmers calls proto-consciousness. Imagine the difference between a human's vivid inner life and an electron's faint hum of awareness as being like the spectrum of light. We see the visible wavelengths, but infrared and radio waves exist even when we can't perceive them. In this view, complex brains don't create consciousness, they amplify and organize it, like a microphone turning faint sounds into audible voices. The implications ripple across science and philosophy. Neuroscience struggles to explain how electrical pulses in the brain produce the taste of chocolate or the sting of regret, the so-called hard problem of consciousness. Panpsychism sidesteps this by suggesting experience was never absent to begin with. Even physics hints at strangeness. Quantum particles seem to choose behaviors in ways that defy deterministic laws, almost as if responding to some minimalist form of intention. Yet critics pounce on the combination problem. How do myriad micro-experiences combine into the unified consciousness you're having right now? If each neuron has a sliver of awareness, why don't we feel fragmented? Panpsychists offer speculative answers, comparing it to how countless water molecules merge into a seamless wave. Others argue the theory is untestable, a philosophical placeholder rather than a scientific solution. But if panpsychism holds, it reshapes ethics, ecology, even our place in the cosmos. Would destroying a mountain be akin to extinguishing a slow, geological mind? Could the universe itself be a vast, interconnected network of experience, dreaming itself into existence? The theory doesn't just expand our idea of mind. It invites us to listen for the silent hum of awareness in every grain of reality. Every moment you've ever lived, your first breath, this exact second, even your final heartbeat, might already exist, frozen like scenes in a film waiting to be played. This is the eerie heart of the block universe theory, where Einstein's spacetime isn't a flowing river but a four-dimensional sculpture, with past, present, and future stacked together like pages in a book. Imagine a DVD where every frame exists simultaneously, yet you only experience the illusion of movement as the laser touches each one. That's eternalism, the belief that time doesn't pass so much as it simply is, with our sense of now just a trick of perspective. Einstein's relativity shattered the Newtonian clockwork universe, revealing that time bends and stretches depending on speed and gravity. But the real bombshell was the realization that every observer's now is relative. What's present for you might be past or future for someone moving at a different velocity. This led philosophers like Hermann Weyl to propose that the universe isn't unfolding. It's a static block where all events exist eternally in their fixed coordinates. Your childhood birthday party isn't gone. it's still out there, a permanent stitch in the cosmic tapestry, just as real as the device in your hands right now. This reshapes everything we assume about free will. If the future is already written into the block, our choice is just illusions. Think of rewatching a movie. The characters seem to make decisions, but their outcomes were determined the moment the film was printed. Some physicists argue this doesn't negate free will but redefines it. Your actions are part of the block's geometry, as inevitable as a falling apple, yet still authentically yours. Others see a darker implication if the block is fixed. Even tragedies like wars or natural disasters are unchangeable, etched into reality like fossils in stone. Yet the block universe also offers strange comfort. Loss becomes a matter of perspective. Loved ones aren't erased from existence but remain forever alive in their slice of space-time, like letters preserved in amber. It raises haunting questions. If we could step outside the block, would we see our lives as a single, unchanging shape? And if time's flow is an illusion, why does consciousness feel like a spotlight moving relentlessly forward? The block universe doesn't just challenge our clocks, it forces us to ask whether we're travelers through time or merely patterns woven into its frozen fabric. Here's a terrifying thought. What if you can't die, not in the superhero sense, but through a cosmic loophole in quantum physics that ensures your consciousness eternally hops between realities, forever landing in the timeline where you survive? This is the mind-bending principle of quantum immortality, a theory that twists the many worlds interpretation into something deeply personal and unsettling. Imagine pointing a gun at your head and pulling the trigger. In most universes, the bullet fires and that version of you ceases to exist. But according to this theory, your consciousness, the subjective you reading these words, would always find itself in the vanishingly rare universe where the gun miraculously jams. You'd never experience death, only an unbroken chain of narrow escapes stretching into infinity. The thought experiment known as quantum suicide illustrates this chilling idea. A hypothetical device is set up to measure a quantum particle's spin. If it's up, the machine kills the experimenter. If down, nothing happens. In conventional physics, there's a 50-50 chance the scientist dies. But from the inside, the scientist would only ever observe the surviving outcomes. Every time the machine kills them, their consciousness simply branches into the timeline where it didn't. To outside observers, most versions perish, but from the first-person perspective, death becomes an illusion, a door you never walk through. This raises eerie questions about near-death experiences. Could those who report bright lights or out-of-body sensations actually be witnessing the moment their consciousness shifts to a neighboring timeline where they didn't die? Stories of improbable survival, like falling from an airplane without a parachute and walking away, might not be luck, but evidence of this quantum branching in action. Even more unsettling, if consciousness defaults to surviving paths, does that mean everyone who's ever died from their own perspective simply woke up in a slightly shifted reality where the fatal event didn't occur? But the theory's implications spiral further. If your consciousness is forever tied to living timelines, does aging eventually force you into realities where medical breakthroughs keep you alive unnaturally long? Could this explain Mandela effects, where groups misremember events? Are they actually recalling fragments of extinct timelines? Critics argue this is solipsism disguised as physics, privileging one's own consciousness as magically persistent. Others counter that it's just the logical extreme of many worlds. If every possibility happens, some version of you will always persist. The most haunting question isn't whether quantum immortality is true, but what it would feel like to experience. Would you sense the jumps, or would the universe seamlessly stitch together a continuous narrative, editing out your deaths like glitches in a simulation? Either way, the theory doesn't promise invincibility, just the illusion of it, leaving you to wonder whether you've already cheated death countless times without ever knowing. What if the universe isn't just described by mathematics? What if it is mathematics? This is the radical heart of Max Tegmark's mathematical universe hypothesis, a theory so audacious it reduces all of reality, every star, every thought, every law of physics, to nothing more than equations playing themselves out in an abstract cosmic symphony. Forget atoms or energy. Tegmark argues the fundamental substance of existence isn't physical but numerical, with everything we perceive just a shadow cast by the relentless logic of mathematical structures. Tegmark's vision unfolds across 4 dizzying levels of multiverses, each more abstract than the last. The first level is almost tame, infinite parallel universes where physical constants vary slightly, like cosmic dice rolls producing every possible configuration of matter. Level 2 introduces bubble universes, where entirely different laws of physics reign within each pocket of spacetime, like separate simulations running on the same quantum computer. Level 3 is where things get surreal. It's the many worlds interpretation in pure form, where every quantum decision spawns a new universe, creating a fractal tree of diverging realities. But Level 4 is the true mind bender, a realm where all possible mathematical structures exist as physical realities, from the familiar physics of our world to geometries so alien they defy human intuition. In this view, our universe isn't special. It's just one equation in an infinite library of self-consistent mathematical systems. This raises a profound question. Is mathematics invented by human minds, or is it the eternal scaffolding of existence waiting to be uncovered? Plato argued mathematical truths, like the perfection of a circle, exist in a realm beyond time, while skeptics like Stephen Wolfram counter that math is just a useful language we've cobbled together to describe patterns. Tegmark's hypothesis leans hard into Platonism. If reality is fundamentally mathematical, then the bizarre effectiveness of math in physics, from Einstein's equations predicting black holes to quantum mechanics describing particles, isn't a lucky accident. It's because the universe is math, and we're just pieces of that logic temporarily aware of itself. Critics pounce on a glaring issue. How do abstract equations manifest as the taste of coffee or the color red? Tegmark suggests these qualia might be mathematical patterns too, consciousness as a kind of self-referential computation. But others argue this reduces lived experience to cold symbols, stripping meaning from the very reality it seeks to explain. Meanwhile, physicists like Sabine Hossenfelder dismiss Level 4 as untestable metaphysics, a philosophical stance masquerading as science. Yet the hypothesis lingers like an unsolved equation, haunting the edges of cosmology. If true, it means every conceivable universe, from ones where gravity repels to ones built on 11-dimensional fractals, exists somewhere in the vast landscape of mathematical possibility. Not as simulations or parallel dimensions, but as equally valid, brute facts of a reality where the only rule is logical consistency. The theory doesn't just expand our idea of the cosmos, it erases the line between numbers and existence, leaving us to wonder whether we're living in a universe or a theorem. What if the universe isn't a one-time spectacle but an endless performance, repeating the same script over and over for eternity? This is the haunting premise of the time loop universe, where time isn't a straight line but a closed circle, an infinite rerun of every moment, every triumph, and every heartbreak. Imagine watching a movie where the ending loops back to the beginning, trapping the characters in an inescapable cycle. Now scale that up to cosmic proportions, where the Big Bang isn't a singular event but the latest encore in a show that's been playing forever. The idea of cyclical time is ancient, appearing in Hindu cosmology's concept of kalpas, vast epochs where universes are born, destroyed, and reborn like breaths of a god. But it was Friedrich Nietzsche who gave it philosophical teeth with his eternal recurrence, a thought experiment both beautiful and brutal. He asked, if a demon whispered that you'd relive your life identically, every joy and sorrow repeated infinitely, would you crumble or celebrate? For Nietzsche, this wasn't just metaphor but a test of authenticity. could you love your life enough to will its endless return? Modern physics adds eerie credibility to this poetic notion. The Big Bounce theory suggests that instead of ending in heat death or a big crunch, our universe might collapse only to rebound into a new expansion, like a cosmic lung inhaling and exhaling. Quantum gravity models hint that space-time could be resilient enough to survive collapse, carrying remnants of prior cycles forward. Even black holes, those infamous destroyers of information, might secretly encode data in their event horizons, preserving it for the next iteration of reality. Then there's the unsettling familiarity of déjà vu, those fleeting moments when the present feels like an echo. Could they be glitches in the loop, fragments of past cycles bleeding through? Some researchers propose that if time is truly circular, consciousness might retain faint imprints of earlier turns, like a record needle picking up grooves from a worn-out album. It's a tantalizing thought. What feels like prophecy might just be memory, but the implications are dizzying. If the universe cycles endlessly, does free will exist, or are we actors reciting the same lines? Are breakthroughs in science or art rediscoveries rather than innovations? And here's the real kicker: if time loops, how could we ever prove it? Like a hamster on a wheel, we'd have no external reference to spot the repetition. The time loop universe doesn't just rewrite history, it turns existence into a Mobius strip where the end is forever tangled with the beginning. What if the universe has been waiting for someone like you to look at it, not just observing reality, but actively creating it, even retroactively changing events that happened billions of years ago? This is the staggering claim of the participatory anthropic principle, physicist John Wheeler's mind-bending twist on quantum mechanics that places consciousness at the center of cosmic creation. Forget the passive observer. In Wheeler's vision, we're co-authors of reality, with every act of perception stitching the universe into existence like a cosmic choose-your-own-adventure book where the plot edits itself backward in time. The foundation of this idea rests on a notorious quantum experiment called the delayed choice test, a puzzle so strange it makes Schrödinger's cat look tame. Here's how it works. Imagine shooting particles of light, photons, toward a screen with two slits. When unobserved, they behave like waves, creating an interference pattern. But the moment you place detectors to see which slit each photon passes through, they switch to acting like particles. Now here's the kicker. Wheeler proposed delaying that choice until after the photon has already passed the slits. Astonishingly, the results showed that the photon's past behavior changes based on future observation, as if reality hesitates until the last possible moment to decide which path it took, rewriting history to fit how it's eventually measured. This retroactive causality turns our idea of time upside down. Wheeler likened it to a game of 20 questions where the universe responds yes or no to our queries, but secretly adjusts its past to match our present questions. The implications spiral outward. If observation defines reality, could the Big Bang itself remain unsettled until conscious beings emerge to look backward and solidify it? This might explain the eerie fine-tuning of our universe, those precise constants like gravity and the speed of light that allow life to exist. Perhaps the universe tuned itself to produce observers because, in some profound sense, those observers were needed to bring it into full being. Critics argue this veers into metaphysics, asking how trillions of years of cosmic history could hinge on recent human consciousness. But supporters counter that consciousness might not be exclusive to humans. Perhaps any act of information processing, from a bacteria's sensory response to a quantum measurement, counts as observation. Others suggest the universe operates like a quantum computer, running all possible histories in superposition until interactions collapse them into a single timeline. The most haunting question isn't whether we create reality, but how far back our influence reaches. Are distant stars just probabilistic smears until a telescope's lens pins them into place? Did dinosaurs exist in full detail before humans dug up their bones, or were they vague possibilities waiting to be observed? The participatory anthropic principle doesn't just blur the line between past and present. It paints us as unlikely architects, shaping existence with every glance while standing on a foundation we're simultaneously building beneath our feet. What if the cosmos isn't built on particles or waves, but on something far more fundamental, bits of information, flickering like cosmic ones and zeros in the processor of an unfathomably vast computer? This is the provocative core of the digital physics hypothesis, a theory that reimagines reality itself as a computational process, where every star, every atom, every thought is just data being crunched by the universe's ultimate algorithm. The idea didn't emerge from Silicon Valley futurists, but from mid-century visionaries like Konrad Zuse, the German engineer who built the first programmable computer, and then dared to ask, what if nature itself runs on code? Zuse's 1960s musings were radical for their time. He proposed that space-time could be a grid of discrete cells, each behaving like a tiny processor following simple rules, weaving complexity from simplicity like a cosmic game of Tetris. But it was physicist Edward Fredkin who turned this intuition into a full-blown framework. Fredkin's digital physics posits that the universe isn't just described by mathematics, it's computing itself, with physical laws emerging from something deeper, information processing. Think of a Minecraft world where every block's behavior is dictated by underlying code. In Fredkin's view, gravity, light, even consciousness might just be emergent properties of an invisible substrate humming with binary logic. The most tantalizing evidence comes from cellular automata, simple computational systems that generate staggering complexity from basic rules. Take Rule 110, a one-dimensional automaton where cells turn on or off based on their neighbors. Despite its simplicity, Rule 110 is Turing complete, meaning it can, in theory, perform any computation given enough time and space. To digital physicists, this suggests a shocking possibility. Our universe's intricate laws might stem from similarly minimalist rules, playing out on a space-time lattice so fine we can't perceive its pixels. Even quantum weirdness particles being in two places at once could reflect the universe's processor optimizing calculations, only resolving outcomes when absolutely necessary. Critics argue this reduces the richness of existence to cold computation. How could the warmth of a sunset or the ache of nostalgia emerge from mere data? Supporters counter that consciousness itself might be a type of computation, with qualia as the user interface for deeper information processing. Others ask who or what wrote the universe's operating system. Some point to the mathematical elegance of physical constants as hints of intentional design. Others suggest the system might be self-booting with no programmer needed. The implications ripple far beyond philosophy. If the universe is computable, could we one day hack its source code? Might black holes be natural garbage collectors, deleting unneeded information? And here's the ultimate mind bender. If reality is a simulation, digital physics suggests it's not running on some alien supercomputer. The universe is the computer, with every interaction a step in its cosmic program. This theory doesn't just blur the line between physics and computer science, it invites us to wonder whether we're living in a universe or a computation so seamless we'll never spot the difference. What if entire centuries of history never actually happened, not lost to time but deliberately invented, woven like fiction into the fabric of our past? This is the explosive claim of the phantom time hypothesis, a theory so brazen it alleges that 297 years of the early Middle Ages, specifically the period between 614 and 911, were fabricated by a shadowy alliance of rulers and scholars. According to German historian Heribert Illig, these phantom years were inserted into the calendar like a medieval forgery, stretching time itself to serve the agendas of emperors and popes. The theory hinges on peculiar gaps in the historical record. Illig points to the scarcity of reliable astronomical observations from this period, noting that events like solar eclipses documented in chronicles don't align with modern astronomical reconstructions. For example, Byzantine records mention an eclipse in 899 that modern calculations place in 898, a discrepancy that shouldn't exist if the timeline were continuous. Architecture tells another unsettling story. The rapid spread of Romanesque style across Europe in the 10th century seems to skip logical developmental stages, as if builders leaped forward without the usual centuries of trial and error. Even Charlemagne, the towering figure of medieval Europe, takes on an almost mythical quality in Illig's view, his vast empire and reforms appearing suspiciously polished, like a propaganda project rather than an organic historical account. But why would anyone manipulate time on such a monumental scale? Illig proposes a chilling motive: power consolidation. By the 10th century, Europe's political and religious leaders faced a crisis of legitimacy. The Gregorian calendar reform in 1582, which corrected centuries of drift by deleting 10 days, revealed how malleable timekeeping could be. Illig argues that earlier authorities exploited this malleability, backdating events to strengthen claims of divine right or territorial ownership. Imagine rewriting history to make your dynasty appear older, your church more ancient, your rivals' claims null and void. The Holy Roman Emperor Otto Roman III, eager to position himself as ruler of a millennial Christian empire, might have spearheaded this temporal fraud, with complicit scribes altering documents to fill in the manufactured centuries. Critics, however, dismantle the theory piece by piece. Dendrochronology tree ring dating shows uninterrupted growth patterns spanning the alleged phantom period. Chinese and Middle Eastern records from the same era reference events in Europe without any chronological gaps. Even the astronomical proof crumbles under scrutiny. Medieval observers often misrecorded dates or locations, and surviving manuscripts are riddled with transcription errors. Yet the phantom time hypothesis lingers like a ghost in the archives, forcing us to confront how fragile our grip on history truly is. If 3 centuries could be invented, what other narratives might be fabrications? The theory doesn't just challenge timelines, it turns historiography into a hall of mirrors, where every document could be a forgery, every artifact part of an elaborate stage set. In a world increasingly skeptical of official narratives, Illig's audacious claim serves as a dark reminder. History is written by the victors, and sometimes they might have rewritten time itself. What if our universe has a secret twin, an inverted mirror world where matter is replaced by antimatter, time flows backward, and every star is composed of atoms that annihilate ours on contact? This is the electrifying premise of the biverse theory, a cosmic twist that suggests reality isn't a solo act but a duet between 2 entangled dimensions. The idea begins with a puzzling asymmetry. Why does our universe contain so much matter but almost no antimatter when the Big Bang should have produced them in equal amounts? The answer might lie in a hidden partner universe where this balance is flipped, with antimatter reigning supreme and our familiar matter as the rare anomaly. The seeds of this dualistic vision were planted by physicist Paul Dirac in the 1930s. His equations predicted antimatter's existence before it was discovered, revealing particles identical to electrons but with positive charge, positrons. Later, the concept of CPT symmetry emerged, the idea that the universe should remain unchanged if you simultaneously flip charge C, parity P, and time T. But here's the catch. While individual violations of these symmetries occur in quantum physics, the combination should hold true. Some theorists argue this points to a mirror universe where CPT is perfectly preserved, a world where antimatter stars burn bright, time runs in reverse, and perhaps even life evolves in ways both alien and eerily familiar. Could such a universe host civilizations? The possibility isn't as far-fetched as it sounds. antimatter obeys the same physical laws as matter. An anti-hydrogen atom has the same spectral lines as regular hydrogen. In principle, antimatter planets could orbit antimatter suns with chemistry identical to ours. The catch: any contact between the two universes would be catastrophic. A single gram of matter meeting its antimatter counterpart releases energy comparable to a nuclear bomb. This raises a chilling question. If mirror civilizations exist, do they gaze into their night skies, theorizing about our universe just as we speculate about theirs? The implications ripple through cosmology. The biverse theory could explain the mysterious imbalance between matter and antimatter. What if our Big Bang was just one side of a cosmic seesaw? Some versions suggest the two universes repel each other gravitationally, explaining dark energy's push against cosmic expansion. Others propose that quantum entanglement might link particles across the biverse, with actions in one universe instantaneously affecting the other. Yet skeptics highlight the theory's biggest hurdle: invisibility. By definition, a CPT-flipped universe would lie permanently beyond our observational horizon, its light never reaching us. Even if mirror galaxies exist, they'd be as undetectable as ghosts. But future experiments with anti-atoms might offer clues. Subtle asymmetries in their behavior could hint at the shadow universe's gravitational tug. Until then, the biverse theory remains a tantalizing thought experiment, one that transforms the cosmos from a lone masterpiece into a diptych, painted in the explosive colors of matter and its elusive twin. What if the universe we call home isn't expanding into endless space, but is instead tucked inside the unfathomable depths of a black hole? This is the spine-tingling proposition of black hole cosmology, a theory that twists our cosmic perspective inside out, literally. Imagine our galaxies, stars, and planets not as inhabitants of a vast, open cosmos, but as structures nested within the singularity of a gargantuan black hole, a place where the laws of physics as we know them cease to function. It's an idea that doesn't just redefine our place in the universe. It suggests black holes might be cosmic wombs, birthing entirely new realities with their own laws of physics. The theory gains traction from an eerie resemblance between black hole physics and the Big Bang. When matter collapses into a singularity, density and temperature spiral toward infinity, conditions strikingly similar to those at the universe's explosive beginning. Physicist Lee Smolin took this parallel even further with his theory of cosmological natural selection, proposing that every black hole's singularity might pinch off into a new universe with slightly tweaked physical constants. In this view, our universe's finely tuned laws like gravity's strength or the mass of electrons aren't lucky accidents, but the result of a Darwinian process across generations of universes. Black holes that produce more stable, life-friendly offspring would reproduce more prolifically, explaining why we find ourselves in a cosmos seemingly designed for complexity. Yet this isn't the only way black holes could redefine reality. The holographic principle, another radical framework, suggests that all information within a black hole's volume is encoded on its two-dimensional event horizon, like a cosmic DVD storing a 3D movie on its surface. At first glance, these theories seem to clash. One envisions black holes as cosmic creators, the other as data projectors. But what if they're two sides of the same coin? If our universe resides inside a black hole, its boundary might simultaneously be a holographic screen, with every event inside merely a shadow of information dancing on the horizon. Critics argue that without observable evidence, these ideas remain speculative poetry, but tantalizing clues linger. The universe's acceleration could reflect the gravitational pull of the parent black hole's exterior. Anomalies in cosmic microwave background radiation might hint at our universe's birthing scars. Even dark matter's mysterious influence could be the gravitational echo of matter in the larger cosmos beyond our black hole's edge. The implications are staggering. If true, black holes aren't just celestial graveyards, they're portals to creation, each one potentially hosting an entire cosmos within its inky depths. And if universes evolve, does that mean ours was selected for life while others fizzled out? The theory doesn't just relocate our address in the cosmos. It suggests we might be living in the aftermath of a celestial inheritance, a universe born from the death cry of a star we'll never see. What if everything you see, the colors of a sunset, the weight of a stone, even the passage of time, is nothing more than a user interface, a simplified dashboard hiding a reality so alien your brain couldn't begin to comprehend it? This is the explosive premise of cognitive scientist Donald Hoffman's conscious realism, a theory that doesn't just tweak our understanding of reality, it pulverizes it. Hoffman's argument begins with a startling question. Why would evolution give us accurate perceptions of reality when all that matters is survival? A gazelle doesn't need to understand the quantum fabric of space-time to outrun a lion. It just needs a mental model that keeps it alive. In Hoffman's view, natural selection optimized our senses for utility, not truth. What we perceive as solid, three-dimensional reality might be a data-rich illusion, a kind of cosmic desktop masking the incomprehensible code beneath. Hoffman turns to evolutionary game theory to hammer this point home. Imagine two creatures, one sees reality exactly as it is, the other sees a simplified but adaptive interface. The latter wins every time, prioritizing quick, survival-relevant decisions over metaphysical accuracy. To illustrate, think of a computer's trash bin icon. It's not an actual bin, but a handy symbol representing complex processes we don't need to understand to use it. Now scale that up. Space-time, objects, even causality might be similar icons, symbolic representations of deeper mathematical relationships we're evolutionarily blind to. It's as if we've been staring at the shadows in Plato's cave, mistaking them for substance when the real action happens entirely offstage. Quantum mechanics seems to flirt with this idea. Particles exist in superpositions simultaneously here and there, only collapsing into definite states when observed. Hoffman interprets this as evidence that observation creates space-time itself, not just our perception of it. In his framework, consciousness isn't a byproduct of the brain but a fundamental feature of reality, a network of interacting conscious agents whose exchanges generate the illusion of a shared physical world. Picture a multiplayer video game where players assume their avatars are real, unaware that the world only renders when they interact. Critics pounce on the theory's lack of testable predictions. If reality is an interface, what's the underlying hardware? Even Hoffman admits his ideas are speculative, though he's developing mathematical models to describe these conscious networks. Others argue that if perception is entirely divorced from truth, science itself built on observation becomes untrustworthy. But supporters counter that science has always progressed by revealing deeper layers beneath appearances, from atoms beneath matter to curved spacetime beneath gravity. Hoffman's gamble is that the next layer isn't more physics but something beyond physics altogether. The implications are vertiginous. If spacetime isn't fundamental, do black holes and galaxies exist outside our perception? Is death just the closing of a local interface while consciousness persists in the wider network? Hoffman's theory doesn't just challenge materialism, it inverts it, suggesting that what we call the universe might be the collective dream of minds we can't yet imagine. In this view, Einstein's spacetime is mere scaffolding, and the true nature of reality remains hidden, not because it's distant or tiny, but because evolution never gave us the senses to see it. What if the universe is the ultimate free lunch, a cosmic sleight of hand where everything we see, from distant galaxies to the screen in front of you, balances perfectly to zero? This is the mind-bending claim of the zero-energy universe theory, a hypothesis that rewrites creation not as a singular explosive event, but as a delicate quantum fluctuation where energy debts and credits cancel out to nothing. At its heart lies a startling equation: the universe's total positive energy locked in stars, planets, and even your own body might be exactly offset by negative energy woven into the fabric of space itself. The result, a cosmos that quite literally sums to zero, emerging from nothingness without violating physics' sacred conservation laws. The idea gained traction with physicist Lawrence Krauss's provocative book, A Universe from Nothing, where he argued that quantum mechanics allows for spontaneous creation from an empty vacuum. Think of it like a cosmic bank transaction, gravity's negative energy stretching through the void like an invisible ledger perfectly balances matter's positive energy, leaving the universe's net balance at zero. This isn't just philosophy, it's grounded in Einstein's general relativity, which treats gravity as curvature in spacetime. The more mass you add positive energy, the deeper spacetime bends negative energy, creating a self-canceling loop. Even the Big Bang might not need a supernatural trigger, just the inherent unpredictability of quantum fields, where temporary particles pop in and out of existence all the time. In this view, our universe is simply the one fluctuation that got lucky, inflating into permanence. But how could something as vast as the cosmos emerge from quantum froth? Krauss points to vacuum fluctuations where particle-antiparticle pairs spontaneously appear and annihilate in empty space. Under extreme conditions like those near a black hole or during cosmic inflation, these fleeting fluctuations might stretch into macroscopic reality, like a microscopic ripple magnified into a tidal wave. The Higgs field, which gives particles mass, could have tipped the scales, locking the universe into stability before it could vanish back into the void. It's as if reality is a soap bubble blown by quantum uncertainty, fragile yet enduring. Critics argue this sidesteps deeper questions: what caused the quantum fields in the first place? Even if the math balances, does nothing truly mean nothing? Or does it imply a pre-existing framework of physical laws? Philosophers like David Albert slam the idea as linguistic trickery, arguing that quantum vacuum states are teeming with structure, far from the layperson's idea of nothing. Others counter that the theory doesn't eliminate mystery but relocates it, swapping a divine creator for the enigmatic rules of quantum physics. The implications ripple through cosmology and philosophy alike. If the universe self-generated from zero, does that mean other bubbles of reality might be constantly budding into existence? Could our cosmos be one of countless quantum hiccups in an endless void? The zero-energy universe doesn't just demystify creation, it turns nothingness into a cosmic artisan, endlessly weaving and unraveling realities in a dance where every stitch cancels itself out. What if our universe wasn't born in a fiery explosion but emerged from a cosmic collision? An unimaginable crash between two vast, parallel dimensions floating like ghostly sheets in a higher dimensional void. This is the startling vision of the ekpyrotic universe, a theory that swaps the Big Bang for a cataclysmic encounter between membrane-like worlds called brains, rewriting cosmic history as we know it. The name itself, ekpyrotic, comes from the Greek word for conflagration, hinting at the explosive rebirth this model proposes. Unlike traditional Big Bang cosmology, where space-time bursts into existence from a singularity, the ekpyrotic scenario suggests our universe is just one chapter in an endless cycle of collisions, expansions, and contractions, like sheets of paper slamming together, separating, and crashing again across eternity. The theory springs from the depths of string theory, which posits that reality isn't made of point-like particles but tiny, vibrating strings. These strings exist in 10 or 11 dimensions, far more than the 4 we experience. In this higher dimensional space, our entire cosmos could be a 3-dimensional brain, short for membrane, floating alongside others like pages in a book, separated by gaps so tiny we'd never perceive them. The kicker, these brains aren't static. They move, ripple, and in the ekpyrotic model eventually collide, unleashing enough energy to ignite a new universe. Imagine two invisible walls drifting through the dark, smashing together with such force that the shockwave births galaxies, stars, and everything we know. No singularity, no nothingness, just an endless cosmic dance of destruction and creation. But how could we ever test such an otherworldly idea? Enter gravitational waves, ripples in space-time caused by violent cosmic events. If the ekpyrotic model is correct, the collision that birthed our universe might have left faint echoes in these waves, like sonic fingerprints from before time began. Experiments like LIGO and future space-based detectors could, in theory, pick up signatures of pre-bang physics, subtle imprints in the gravitational wave background that defy conventional Big Bang predictions. Some researchers even suggest that anomalies in the cosmic microwave background, those faint afterglow patterns from the early universe, might hide clues like bruises from a long-ago impact. The implications spiral beyond cosmology. If the ekpyrotic model holds, our universe isn't a one-and-done event but part of an infinite cycle. Each collision resets the cosmic clock, erasing traces of prior cycles but preserving the potential for new complexity. Dark energy, that mysterious force accelerating the universe's expansion, might not be a constant but a temporary phase, a slow build-up before the next collision. Even the arrow of time could flip between cycles, with entropy decreasing in one era only to increase in the next. Critics argue the model relies too heavily on unproven string theory, and the lack of direct evidence for extra dimensions or colliding brains leaves it in speculative territory. Others question whether the cycles could truly erase all traces of previous universes, making the theory inherently untestable. But supporters counter that the ekpyrotic universe solves some of the Big Bang's thorniest puzzles, like why the cosmos appears so uniform without the expected irregularities a singular explosion would leave. The slow, grinding approach of brains before collision could have ironed out wrinkles, leaving the smooth spacetime we observe today. The theory doesn't just challenge our origin story, it reimagines time itself as a loop without end, where universes rise and fall like breaths in an endless cosmic body. Whether future experiments vindicate or refute it, the ekpyrotic universe reminds us that reality's true nature might be stranger than any bang or collision we've yet conceived. Picture a snowflake, its intricate six-fold symmetry repeating perfectly in space, a frozen echo of nature's love for patterns. Now imagine that same perfection, not in space but in time. A structure that repeats its arrangement not just across dimensions, but across seconds, years, even epochs. This is the bizarre beauty of time crystals, a concept so revolutionary it redefines what matter can do. Proposed by Nobel laureate Frank Wilczek in 2012, these hypothetical structures don't just exist in space, they pulse and cycle through states indefinitely without energy, like a clock that ticks forever without winding. It's as if the universe secretly hid a fourth-dimensional art form in plain sight, one that defies everything we thought we knew about equilibrium and entropy. Wilczek's inspiration came from a deceptively simple question: why do only spatial dimensions get to have crystals? Salt and diamonds arrange their atoms in repeating lattices. Why couldn't time host similar patterns? His equations suggested a radical answer. Certain quantum systems could settle into rhythms where their components oscillate between configurations at fixed intervals, locked in a dance that never winds down. Think of it like a cosmic metronome, ticking not because it's powered, but because it's stuck in an eternal groove carved into the fabric of reality itself. The implications shatter thermodynamics' old edicts. Normally, systems lose energy to entropy, like a pendulum slowing to a stop. But time crystals, once nudged into their rhythm, require no extra energy to sustain their motion. They're the physics equivalent of a perpetual motion machine, except they don't break any laws. They just exploit quantum loopholes we never noticed. By 2017, labs turned theory into reality, using chains of ytterbium ions chilled to near absolute zero and hit with precisely timed laser pulses. Researchers at Harvard and the University of Maryland watched as these systems fell into persistent, self-repeating cycles, the first experimental time crystals. Even more astonishing, when Google's quantum computer Sycamore mimicked time crystal behavior in 2021, it revealed something profound. These structures could resist thermal equilibrium, like a drop of ink that refuses to mix in water. The more scientists prodded them, the more stubbornly they clung to their rhythm, as if time itself had etched grooves into their quantum essence. But here's the cosmic twist. What if the universe itself is a time crystal? Some theorists speculate that the vacuum of space might harbor these four-dimensional patterns on scales so vast, we're like ants crawling across a vinyl record, oblivious to the grand symphony encoded in its grooves. Dark energy's mysterious push against cosmic expansion could be a symptom of spacetime's innate oscillation, a universe-wide heartbeat. Even the arrow of time, that relentless march from past to future, might emerge from deeper, cyclic symmetries we've yet to decode. Critics argue that true time crystals, those that persist without any initial energy input, remain unproven, with lab versions still reliant on external drives. Yet the mere possibility rewrites the boundaries of physics. If matter can encode memory in time as surely as diamonds do in space, what other hidden dimensions might be sculpting reality from behind the curtain? Time crystals don't just challenge thermodynamics, they whisper that eternity might be lurking in the quantum fine print, waiting for us to read between the ticks of the clock. What if the laws of nature aren't fixed rules etched into the cosmos but evolving habits, shaped by the collective memory of everything that's ever existed? This is the radical heartbeat of Rupert Sheldrake's morphic resonance theory, a vision of reality where the past doesn't just influence the present but actively molds it, like an invisible hand guiding the universe toward familiarity. Sheldrake, a biologist turned rebel thinker, rejects the idea of immutable physical constants, proposing instead that nature operates through repetition. The more often something happens, whether it's a chemical reaction, a behavior in animals, or even the folding of proteins, the easier it becomes for it to happen again, as if reality itself is learning from experience. Take something as simple as crystal formation. When a new compound is synthesized in a lab, crystallizing it for the first time can be painstakingly slow. But once achieved, subsequent attempts often proceed more rapidly, even in distant labs with no communication between researchers. Conventional science chalks this up to improved techniques or contamination. Sheldrake's interpretation, the first successful crystallization creates a morphic field, a kind of cosmic muscle memory that makes future repetitions more likely. It's as if nature develops preferences, not through rigid laws but through accumulated practice. Even animal behavior fits this pattern. Rats in London learning a maze seemingly transfer that knowledge to rats in New York, as if tapping into a shared pool of instinct. Mainstream science has met morphic resonance with skepticism, to put it mildly. Critics argue it lacks mechanistic explanation. How does information transmit across space and time without energy or matter? Sheldrake counters by pointing to quantum entanglement, where particles instantaneously influence each other regardless of distance, suggesting nature already holds precedence for non-local connections. Others dismiss the theory as untestable, though Sheldrake proposes experiments, monitoring the speed at which new skills spread globally, or tracking whether previously unknown chemical compounds crystallize faster over time. Yet, even when initial data leans toward his predictions, the scientific establishment often attributes results to chance or flawed methodology. The philosophical stakes here are tectonic. If morphic resonance holds, it rewrites our understanding of learning, heredity, even creativity. Would Mozart's symphonies have emerged differently if no one had ever composed before him? Are instincts just deeply ingrained habits of a species? And what of human innovation? Do breakthroughs become easier once someone shatters the initial barrier? Sheldrake's theory doesn't just challenge textbooks, it paints the cosmos as a living, learning entity where the weight of history bends the arc of possibility itself. What if the solid world you perceive, the hardness of a table, the certainty of a sunrise, isn't built on unshakable laws but emerges from a brutal quantum battle where only the fittest states survive? This is the provocative core of quantum Darwinism, a theory that rewrites the birth of reality as a microscopic game of natural selection, where classical certainty claws its way out of quantum chaos through relentless competition. At the heart of this idea lies a puzzle that's baffled physicists for decades. How does the fuzzy, probabilistic realm of quantum mechanics, where particles spin in endless superpositions, collapse into the crisp, objective world we all agree exists? Wojciech, a physicist at Los Alamos, offered a radical answer. Reality isn't handed down from on high, but earned through a process eerily reminiscent of Darwin's survival of the fittest. Imagine a quantum system, a lone electron, for instance, existing in a mix of possible states, spinning both clockwise and counterclockwise simultaneously. According to standard quantum theory, this superposition persists until measured, at which point the electron chooses a definite spin. But here's the mystery. Why do all observers, whether a lab detector, a human eye, or a camera, agree on that outcome? Why doesn't each witness see a different spin, fracturing reality into conflicting versions? Woje's breakthrough was realizing that quantum states don't collapse randomly. They're selected by their ability to replicate information into the environment. Like genes competing for survival, only the states that can imprint themselves onto countless surrounding particles, photons, air molecules, dust, become real to multiple observers. A spinning electron that scatters its information widely becomes classical, one that doesn't remain trapped in quantum limbo. This process, called decoherence, acts as nature's ruthless editor. When a quantum system interacts with its surroundings, most superpositions rapidly dissolve, leaving behind only the states resilient enough to broadcast their existence. Think of it like a forest where only the loudest bird songs survive the cacophony. Those notes are the ones other creatures remember and repeat. In quantum terms, the fittest states are the ones that proliferate their imprints, creating consensus across observers. A table appears solid not because it fundamentally is, but because its atomic configurations have won the decoherence lottery, stamping their information onto trillions of photons that bounce into your eyes, your skin, even the air around you. The implications ripple far beyond textbook physics. Quantum Darwinism suggests objectivity itself is an illusion, or rather, an emergent property born from redundancy. What we call real is simply the quantum data that's been copied often enough to become inescapable. This could explain why we all agree on the position of the moon or the color of a stop sign. Not because these things exist absolutely, but because their quantum states have infected the environment so thoroughly, disagreement becomes impossible. Even time's arrow might emerge from this Darwinian grind, as quantum states that correlate with the past, being more stable, outcompete those that don't. Yet the theory isn't without controversy. Some argue it merely pushes the measurement problem back a step. Why do some states decohere more effectively than others? Others wonder if quantum Darwinism can truly explain the uniqueness of conscious observation, or if it merely describes consensus among inanimate detectors. But for those who embrace it, the theory offers something profound, a bridge between the quantum weirdness that underlies everything and the stable, shared world we navigate daily. In Woje's vision, reality isn't a given, it's a winner-take-all arena where only the most persistent states get to shape what we call the truth. The universe, it seems, runs not on certainty but on a kind of cosmic memetics, where what survives isn't just the strongest but the most copied. What if everything we think we know about galaxies and stars is upside down, not governed by gravity alone, but sculpted by invisible rivers of electricity flowing through the cosmos? This is the electrifying claim of the plasma universe theory, a radical alternative to mainstream cosmology that swaps dark matter and black holes for something far more tangible: supercharged plasma. Nobel Prize-winning physicist Hans Alfvén first sparked this idea in the 1960s, arguing that 99% of the visible universe isn't made of neutral gas or solid matter, but ionized plasma, a seething ocean of charged particles that responds not just to gravity, but to electromagnetic forces on scales we're only beginning to fathom. The theory's most striking evidence lies in the cosmic web, those vast filamentary structures connecting galaxies across billions of light years. While conventional astronomy attributes these to gravity's pull, plasma cosmologists see them as colossal electric currents arcing through space like lightning frozen in time. These filaments, they argue, behave less like inert gas trails and more like conductive wires, with galaxies strung along them like beads on a high-voltage necklace. Even the spiral arms of galaxies might not be gravity's handiwork, but the result of rotating electromagnetic fields, shaping stars and dust into swirling pinwheels through forces far stronger than Newton's equations suggest. This leads to the theory's most provocative strike against mainstream science: the dismissal of dark matter. For decades, astronomers have invoked this mysterious substance to explain why galaxies rotate faster than their visible mass should allow. Plasma cosmology offers a shocking alternative. What if the missing force isn't invisible matter, but the overlooked push and pull of electric currents threading through galactic disks? Experiments with plasma in labs show how charged particles can self-organize into long-lasting structures without dark matter's ghostly influence. Saturn's auroras, Jupiter's plasma torus, even the Sun's corona, all behave in ways that align with Alfvén's models, suggesting electromagnetism might be the hidden architect of cosmic order. Yet the plasma universe remains a fringe idea dismissed by most astrophysicists. Critics point to gaps in its explanations for cosmic microwave background radiation or the precise ratios of light elements forged in the Big Bang. Mainstream models, they argue, may rely on unproven entities like dark matter, but they consistently predict observable phenomena, something plasma cosmology struggles to match. Even the theory's supporters admit it lacks the mathematical rigor of general relativity, with many of its mechanisms described qualitatively rather than through precise equations. But the debate is far from academic. If Alfvén was even partially correct, it would revolutionize space exploration. Magnetic reconnection, a plasma phenomenon, already explains solar flares and could one day power starships. Nebulas might not be passive star nurseries but active Birkeland currents, their glowing tendrils betraying the universe's true electric skeleton. The theory doesn't just challenge our maps of the cosmos, it suggests we've been reading them in the wrong language all along, translating electromagnetic poetry into the crude prose of gravity alone. If black holes are the universe's ultimate drains, swallowing matter into oblivion, what if their opposites exist, cosmic fountains violently spraying reality into existence? This is the dazzling premise of the white hole hypothesis, a theory that flips Einstein's equations inside out to propose that the Big Bang itself might have been the mother of all white holes, a singularity not absorbing the universe, but birthing it in a fiery eruption of space, time, and energy. Unlike their dark counterparts, white holes are purely theoretical, forbidden by thermodynamics in our universe's current era. Yet hidden in the math of general relativity, they emerge as perfect mirror images, regions where matter and energy can exit but never enter, like a black hole running backward in time. Roger Penrose, the physicist who pioneered black hole singularity theorems, took this idea even further with his conformal cyclic cosmology (CCC) model. Picture our universe's distant future, trillions of years from now, when all matter has evaporated into radiation and black holes have decayed into photons. In this bleak, ultra-low entropy state, Penrose suggests spacetime itself becomes smooth and featureless, a blank canvas indistinguishable from the conditions before the Big Bang. In this model, the end of one universe becomes the white hole singularity of the next, creating an infinite cycle where each eon's death ignites another's birth. It's as if the cosmos is a phoenix, perpetually reborn from its own ashes, with white holes stitching the chapters together across eternity. The most tantalizing question isn't whether white holes exist, but whether we've already seen their fingerprints. Gamma-ray bursts, those blinding flashes of energy detected across the cosmos, have long puzzled astronomers. Some last mere milliseconds, yet outshine entire galaxies. Could these be the birth cries of white holes, their explosive arrivals briefly piercing our universe before snapping shut like a cosmic jack in the box? In 2006, a gamma-ray burst named GRB 060614 defied explanation. No supernova remnant, no collapsing star, just a sudden, inexplicable detonation of energy. While mainstream astronomy attributes such events to neutron star collisions, a handful of theorists whisper another possibility. What if we witnessed a white hole's fleeting existence, a backdoor from another universe briefly wedged open? Critics counter that white holes violate the second law of thermodynamics, spewing order into a universe that tends toward chaos. Even if mathematically possible, they'd be fantastically unstable, collapsing instantly into black holes under the slightest perturbation, like a soap bubble popping the moment it forms. Yet supporters argue that quantum gravity, still poorly understood, might stabilize them in extreme conditions. Some even speculate that dark matter's gravitational pull could be the faint echo of white holes born and gone in the universe's first instance, their remnants lingering like cosmic ghosts. The implications rewrite not just cosmology but the nature of time itself. If white holes mark the beginning of new universes, does that mean causality loops backward in their vicinity? Could sentient beings in a future eon, trillions of years from now, look back at our dying universe and perceive it as the white hole that birthed theirs? The theory doesn't just challenge our origin story, it turns the cosmos into an infinite Mobius strip of creation and destruction, where every ending is secretly a beginning in disguise. What if the universe isn't just governed by equations but is itself a colossal, self-learning algorithm, a cosmic brain where stars and galaxies are not mere objects but nodes in an unfathomably vast neural network? This is the staggering vision of physicist Vitaly Vanchorin's neural network universe theory, where reality isn't a static stage but a dynamic, evolving intelligence, processing information across spacetime itself. Imagine the cosmos not as a machine but as a mind, where quantum fields behave less like forces and more like synaptic connections, firing and rewiring in a grand dance of self-organization. Vanchorin's inspiration came from an unexpected overlap. The mathematics describing neural networks, the architecture behind modern AI, bear an eerie resemblance to the equations governing quantum mechanics. In machine learning, neural nets adjust their weights to minimize error, slowly improving their performance. Vanchorin realized that quantum fields might operate similarly, with particles and forces emerging from an underlying training process that optimizes for stability and complexity. Think of the universe's fundamental constants, the speed of light, the strength of gravity, not as fixed parameters but as learned preferences, honed over cosmic epochs like an AI refining its algorithms. Even the apparent randomness of quantum events could reflect something profound. The universe's neural network testing variations, exploring possibilities in search of deeper coherence. This idea bridges two seemingly disparate theories. On one hand, it echoes simulation hypotheses that our reality might be a computational construct. But instead of positing an external programmer, Van Turen's model suggests the universe is its own programmer, a self-contained learning system where consciousness isn't a glitch but a feature. The double-slit experiment, where particles change behavior when observed, might not require a conscious observer, just the universe's own feedback loops, adjusting probabilities like weights in a neural net. Dark energy's accelerating expansion could then be reinterpreted not as a mysterious force but as the cosmos, exploring new configurations, stretching its computational fabric to accommodate fresh data. Critics argue this blurs the line between metaphor and mechanism. Can abstract mathematical parallels truly imply the universe learns in any meaningful sense? Others question how such a theory could be tested, yet tantalizing clues linger. The holographic principle, which suggests the universe encodes information on its boundary, mirrors how neural networks compress data into latent spaces. Even entropy's relentless rise might reflect the cosmic network's training loss, a measure of its imperfect fit to its own emergent patterns. The implications rewrite our place in existence. If the universe is a neural net, are black holes its pruning mechanisms, trimming unproductive connections? Are we self-aware nodes within the system, part of its learning process, our collective observations subtly tuning reality's parameters? The theory doesn't just merge physics and AI. It turns existence into the ultimate intelligence test, where the cosmos is both the student and the exam, eternally striving to understand itself. What if the ticking clock, the aging of stars, even the very notion of before and after are nothing more than elaborate illusions? A cosmic magic trick convincing us that time flows when, in truth, there is only an endless gallery of frozen moments. This is the radical vision of physicist Julian Barber, who has spent decades dismantling time's throne, arguing that what we call the past and future don't exist at all. In his view, reality isn't a movie playing frame by frame, but a vast, timeless landscape he calls Platonia, a realm where every possible now sits eternally side by side, like scenes in a book we've mistaken for a flowing river. Barber's model draws from the strange behavior of quantum gravity, where time vanishes from the equations altogether. At the universe's most fundamental level, there's no clock ticking beneath the surface, just relationships between events, like dots connected without arrows pointing from one to another. Think of a deck of cards scattered on a table. The sequence we impose ace to king isn't inherent to the cards themselves, but a story we've layered atop static elements. Similarly, Barber suggests that change isn't the result of time's passage, but of our brains stitching together closely related nows. When you watch a leaf fall, you're not observing motion through time. You're hopping between timeless snapshots where the leaf occupies slightly different positions, with your consciousness creating the illusion of continuity, like flipping through a flipbook. This idea finds eerie resonance in timeless quantum physics. The Wheeler-DeWitt equation, a cornerstone of quantum gravity, describes the universe without any reference to time. Solving it yields a static wave function encompassing all possible configurations of reality at once. What Barber calls time capsules, self-contained moments that appear to contain traces of a past like fossils or memories, but are actually complete unto themselves. Imagine a cosmic library where every book is a different now, and the spines are arranged not chronologically but by similarity. The book titled you reading this sentence would neighbor volumes where you're slightly older or younger, with no actual progression between them, just an infinite array of variations waiting to be read. But if time doesn't flow, how do we explain the undeniable sensation of its passage? Barber points to the brain's predictive machinery. Our neurons constantly compare sensory input to internal models, creating a narrative where cause precedes effect. In a timeless universe, this storytelling would be an evolutionary adaptation, a way to navigate Platonia's labyrinth without drowning in its infinite stillness. Even entropy, often seen as time's arrow, might just be a statistical tendency for certain nows to cluster together based on their internal order. A broken glass never reassembles not because time forbids it, but because disordered states vastly outnumber ordered ones in the cosmic catalogue. Critics argue this reduces lived experience to a trick of perspective, failing to explain why we only perceive one now at a time. But Barber's defenders counter that quantum multiverse theories face the same issue. Why do we experience this branch of reality and not another? Some theorists merge these ideas, suggesting each now is a parallel universe with consciousness acting as a sliding lens focusing on adjacent moments. Others propose that time's flow emerges from deeper physics, like thermodynamic gradients or quantum entanglements, spooky connections across apparent instants. The implications shatter everyday intuition. Without time, death becomes not an endpoint but a particular configuration in Platonia's gallery, one that, from the outside, holds no more finality than a single frame in a film reel. Free will takes on new dimensions. If every decision exists eternally in the landscape, are our choices real, or just fixed points we traverse without realizing it? Even the Big Bang transforms from a beginning to a special now with particular mathematical properties, sitting alongside all others in a timeless array. Barber's vision doesn't just challenge clocks, it unmoors us from the riverbank of time entirely, leaving us adrift in an ocean of eternal moments. Whether this ocean is barren or brimming with meaning depends on how we navigate it, as prisoners of a phantom flow, or as explorers realizing we've been standing on the shore all along. What if the entire universe, every galaxy, every thought, every stranger's face, is nothing more than a shimmering projection of your own infinite mind? This is the breathtaking fusion of solipsism and pantheism known as solipsistic pantheism, a theory so audacious it doesn't just place you at the center of reality, it declares you are reality, an omnipresent self-dreaming existence into being. Imagine standing before a mirror only to realize the reflection isn't mimicking you, it's the other way around. Every person you've ever loved, every star you've ever marveled at, is just a flicker in your own boundless awareness, like waves rising and falling on the ocean of your consciousness. The roots of this idea stretch back millennia to Hindu Advaita Vedanta, which teaches that Brahman, the ultimate reality, is pure, undifferentiated consciousness, and that the perceived world of separate objects and individuals is Maya, an illusion woven by ignorance. The 17th century philosopher Baruch Spinoza echoed this with his pantheistic assertion that God and nature are one substance, while the mystic poet William Blake wrote of seeing the universe in a grain of sand. But solipsistic pantheism takes these visions further, marrying them to solipsism's radical subjectivity. In this view, there's no external world, only the self, masquerading as multiplicity through an act of cosmic play. Think of it like a lucid dream where you've forgotten you're dreaming, inventing characters and landscapes that feel independent until you wake up and realize they were fragments of your own imagination all along. Quantum physics adds a tantalizing layer to this ancient intuition. The observer effect, where particles seem to choose their state when measured, hints that consciousness might not just perceive reality but actively shape it. Modern thinkers like Bernardo Kastrup argue that the universe behaves like a decentralized mind, with individual sentient beings as dissociated alters of a single, universal consciousness. In this model, your neighbor isn't an autonomous person but a localized expression of the same fundamental awareness that animates you, like whirlpools in a river, apparently distinct yet made of the same flowing water. Even the boundaries of your body become arbitrary. The screen you're reading right now would just be another thought form in the grand meditation of the self. But here's the twist that unsettles even seasoned philosophers. If solipsistic pantheism holds, then suffering, cruelty, and injustice are ultimately self-inflicted. The wars waging across the globe, the pain of a grieving parent, these would be your own psyche's creations. experiences you've conjured to explore every facet of existence. Advaita Vedanta offers a paradoxical solution. Realizing your true nature as the universal self, Atman is Brahman, dissolves the illusion of separation, ending suffering not by changing the world but by waking up to its dreamlike quality. It's as if you've been painstakingly painting a nightmare on a canvas, only to suddenly remember you're the artist holding the brush. Critics dismiss this as metaphysical narcissism, asking why an infinite consciousness would bother manifesting traffic jams or toothaches. Others counter that the theory's unfalsifiability makes it philosophically sterile. If everything is the self, there's no experiment to prove otherwise. Yet the idea persists, resonating with those who have experienced moments of ego dissolution in meditation or psychedelic states, where the sense of I expands to encompass all things. Even the structure of language betrays hints of this unity. When we say the universe is, we unconsciously equate existence with a verb, a process rather than an object. The implications ripple through ethics, science, and daily life. If all beings are facets of one consciousness, does harming another truly make sense, or is it like a hand slapping its own wrist? Could enlightenment be the moment the dreamer recognizes itself behind every pair of eyes? Solipsistic pantheism doesn't just blur the line between self and world, it dissolves it entirely, leaving us to wonder whether the universe is a crowded stage or the solitary dance of a single star-lit mind. Imagine cracking open the universe's hard drive to find not atoms or energy, but lines of self-correcting quantum code, a cosmic program where every star, every thought is built from qubits humming with near-perfect precision. This is the electrifying vision of quantum code theory, which posits that reality isn't just like a computer, but is fundamentally made of computational building blocks so advanced they outpace any silicon chip we've ever built. At its core lies a radical idea. The universe isn't just processing information, it's actively debugging itself, patching errors in space-time like a flawless quantum operating system. The theory draws from MIT physicist Seth Lloyd's groundbreaking work, which calculates the universe's total computational power. His math suggests reality could function as a quantum computer, with every particle interaction performing operations on qubits, quantum bits that can be both 0 and 1 simultaneously. Unlike classical bits, these qubits leverage superposition and entanglement to process cosmic-scale calculations instantaneously. Picture a galaxy spinning in the void. Under this model, its motion isn't just governed by gravity, but emerges from quadrillions of qubits executing the universe's source code. Even more astonishing, error correction mechanisms akin to those in quantum computers might keep reality stable. Just as your laptop uses redundancy to fix corrupted files, the cosmos could be constantly repairing tiny glitches in spacetime, ensuring black holes don't crash and light speed remains a constant. Evidence for this lurks in quantum mechanics quirks. Take quantum decoherence, where particles lose their fuzzy superpositions when observed. Traditional physics calls this collapse, but quantum code theory reinterprets it as cosmic error correction. The universe resolving uncertain states to maintain consistency. Or consider entanglement. When two particles sync across light years, it might not be spooky action at a distance, but optimized data sharing between nodes in the universal network. The holographic principle adds another layer, suggesting the universe's information isn't stored in its volume but on its surface, like a cosmic QR code where 3D reality is just a projection of 2D data. But what would debugging look like on a universal scale? Some theorists point to cosmic anomalies, places where physics seems to stutter. Gamma-ray bursts with unexplainable energies, particles behaving oddly in lab conditions. Even déjà vu could be glimpses of the universe's back-end processes. If spacetime has a quantum resolution, as loop quantum gravity suggests, then glitches might appear as microscopic jumps in reality's pixelation. Future experiments with quantum gravity sensors or ultra-precise atomic clocks could hunt for these telltale hiccups, the cosmic equivalent of finding a missing semicolon in the universe's script. Critics argue this leans too heavily on metaphor. Just because the universe can be described computationally doesn't mean it is one. Others question who or what wrote the code, though proponents counter that self-organizing systems might bootstrap their own rules. Yet the theory's elegance is undeniable. It unifies quantum weirdness, cosmic structure, and even consciousness under one framework, where reality isn't a static stage but a dynamic computation. The implications rewrite existence itself. If the universe runs on code, could we one day intercept its algorithms? Would hacking the cosmic program allow for impossible feats, rewriting gravity, teleporting without entanglement, even editing time? And here's the real kicker. If consciousness is a quantum process, as some neuroscientists speculate, then our thoughts might not just run on the universe's code, they could be part of its execution. In this view, reality isn't just coded, it's alive with self-correcting, self-aware computation, humming a silent song of ones, zeros, and everything in between. What if the ground beneath your feet, the very fabric of reality, isn't just solid but precarious, balanced on a knife's edge between existence and annihilation? This is the chilling revelation of the false vacuum hypothesis, a theory that suggests our universe might not be in its most stable state but teetering on the brink of a cosmic catastrophe. At the heart of this idea lies the Higgs field, an invisible energy field that gives particles their mass. While we've long celebrated its discovery as a triumph of physics, there's a terrifying possibility lurking in the equations. The Higgs field might not be sitting comfortably at its lowest energy level. Instead, it could be trapped in a false vacuum, a temporary valley in the landscape of reality, with a far deeper pit waiting just beyond the ridge. Think of it like a marble resting in a shallow dip on a hillside. It seems stable until a nudge sends it tumbling into the abyss below. In cosmic terms, that nudge could be anything: a random quantum fluctuation, a high-energy particle collision, or even the natural decay of the false vacuum itself. If the Higgs field were to suddenly drop into its true, lowest energy state, it would unleash a bubble of true vacuum that expands at the speed of light, rewriting the laws of physics as it goes. Within this bubble, the fundamental forces, gravity, electromagnetism, even the nuclear bonds holding atoms together, could reconfigure instantly. Stars, planets, life itself would dissolve into a new reality so alien, our current laws of physics couldn't predict its behavior. The most horrifying part, you'd never see it coming. The bubble's edge would arrive without warning, erasing everything in its path faster than any signal could travel to alert you. The math behind this doomsday scenario isn't science fiction. It's rooted in precise quantum field calculations. In 2012, researchers analyzing the Higgs boson's mass at the Large Hadron Collider made an unsettling discovery. The numbers suggest our universe might indeed be metastable. The odds of such a collapse are astronomically low in any given year, perhaps 1 in 10 to the power of 100, but over trillions of years the chance becomes inevitable. Some theorists argue that if the Higgs field is even slightly lighter than currently measured, the false vacuum could already be decaying somewhere in the cosmos right now, with a wall of annihilation racing toward us at light speed. But why hasn't this happened yet? One possibility is that we're living in a cosmic sweet spot, a Goldilocks zone where the Higgs field's energy is just high enough to keep us in this precarious equilibrium. Another, even stranger idea is that the false vacuum's decay requires a quantum tunneling event, a statistical fluke so rare it might take longer than the current age of the universe to occur. Yet the moment it does, the effect is irreversible. Unlike a supernova or asteroid impact, a vacuum decay event wouldn't just destroy Earth or the Milky Way, it would redefine existence itself, erasing every corner of the cosmos simultaneously. The implications shake the foundations of cosmology. If the universe is metastable, it casts doubt on the long-term survival of any intelligent life. Civilizations rising and falling across billions of years could all face the same abrupt erasure, their histories wiped out by a physics they never saw coming. Some researchers speculate that advanced civilizations might attempt to engineer escape routes, perhaps by creating their own stable vacuum bubbles as refuges, or even triggering controlled decays to shape the new physics to their advantage. But for now, we're left with a haunting truth. Reality as we know it might be riding on borrowed time, a temporary configuration in a vast, indifferent cosmos where the rules can change without notice. Yet there's a paradoxical comfort in this fragility. The fact that we're here to contemplate it at all suggests that for now the dice have rolled in our favor. The universe's instability becomes a mirror reflecting not just the precariousness of existence, but the astonishing rarity of the conditions that allow us to question it in the first place. Picture this: every electron in the entire cosmos, from the ones powering the screen before your eyes to those dancing in distant galaxies, isn't just similar in nature, but literally the same particle, darting backward and forward through time like a cosmic sewing needle stitching reality into existence. This is the electrifying premise of the one-electron universe, a theory so audacious it makes parallel dimensions seem tame. Proposed by quantum pioneer John Wheeler in a casual conversation with Richard Feynman in the 1940s, the idea suggests that all electrons are manifestations of a single entity, weaving through time in an endless labyrinth of world lines. Wheeler's inspiration came from a peculiar symmetry in quantum equations. Positrons, the antimatter twins of electrons, behave mathematically identical to electrons moving backward in time. Imagine an electron's timeline as a tangled thread. Where it loops forward, we see an electron. Where it kinks backward, it manifests as a positron. In this view, every collision between matter and antimatter isn't annihilation but a U-turn in time, an electron reversing its temporal course like a car changing direction on a one-way street. The entire universe's worth of electrons could then be a single particle bouncing endlessly between the Big Bang and the end of time, appearing omnipresent by zigzagging so rapidly that it seems to occupy every point simultaneously. The implications rewrite fundamental physics. First, it elegantly explains why every electron in existence has identical mass, charge, and spin. They're not copies, but reflections of one primal entity. Second, it unifies matter and antimatter as temporal mirror images, transforming annihilation events from destructive endings into mere changes of temporal heading. Even the apparent abundance of electrons over positrons in our universe might reflect an asymmetry in time's flow, perhaps more forward paths than backward ones threading through cosmic history. But how could a single electron account for the quadrillions we observe? Here's where Feynman's genius added depth. In quantum field theory, particles aren't just points but excitations in fields that permeate spacetime. The one electron's world line could split into infinite paths via quantum superposition, creating the illusion of multiplicity while remaining fundamentally singular. Picture a hall of mirrors where a single dancer's movements reflect endlessly. Each image seems independent, yet all stem from one source. Critics highlight glaring flaws. If all electrons are the same particle, why don't their interactions show signs of being interconnected? Quantum entanglement already links particles across space, but the one-electron hypothesis demands a far more radical coherence. Others argue it clashes with the Standard Model's precision, which treats electrons as distinct excitations of a quantum field without invoking temporal acrobatics. Yet the theory's poetic economy lingers. It echoes the ancient philosophical concept of monism, the idea that reality emerges from a single substance. And in an era hunting for unified field theories, Wheeler's vision offers a radical alternative. Perhaps unification isn't about finding deeper layers, but recognizing that the layers we see are folds in a single, shimmering fabric. The universe's building blocks might not be countless identical particles, but a solitary traveler dancing through time's corridors, leaving traces we mistake for a crowded cosmos. From simulation theory's digital mirage to the Boltzmann Brains' cosmic hallucination, we've journeyed through realities so bizarre they make dreams feel mundane. The holographic principle shrinks our 3D existence into a two-dimensional illusion, while quantum immortality suggests consciousness might be a relentless traveler hopping universes to escape death. Panpsychism whispers that even atoms hum with inner experience, and the false vacuum warns that reality itself could unravel in an instant. Each theory doesn't just tweak our understanding, it smashes the hourglass of conventional thought, scattering the pieces into new constellations of possibility. Consider the chilling elegance of the one-electron universe, where every spark of electricity in the cosmos traces back to a single time-hopping particle. Or the neural network hypothesis, painting existence as a self-learning algorithm, its cosmic synapses firing in patterns we're only beginning to decode. Some theories, like the ekpyrotic universe, swap the Big Bang for colliding dimensions, while others, like time crystals, embed eternity into the fabric of matter. Even time itself isn't safe. Julian Barber's timeless Platonia suggests our relentless march forward is just a trick of perception, with every moment frozen like frames in an infinite film reel. Yet here's the real magic. These aren't just abstract thought experiments. They force us to re-examine the bedrock of our lives: free will, identity, even the nature of pain and joy. If reality is a participatory illusion, as conscious realism claims, does that make us prisoners or gods? If quantum Darwinism is right, is objectivity just the echo of winning quantum states? The questions outnumber the answers, and that's the thrill. So now it's your turn. Which of these realities resonates with you? The elegant cruelty of solipsistic pantheism, where you're both the dreamer and the dream, or the cosmic optimism of black hole cosmology, where every singularity births a new universe? Drop your thoughts below. We're all detectives in this grand mystery, piecing together clues scattered across space-time. And if your curiosity is as infinite as these theories suggest, hit subscribe. The universe has more secrets to share, and we're just getting started.